This is a simple true or false question. The matrix A, 1, 2, 3, 0, 0, 0, 4, 5, 6 is invertible. Try to think about how you want to answer and how you want to justify. Pause and come back. Now, this matrix, we observe that the second row is consists of all zeros, and like previously you've actually shown, or you should have shown, that if you have a row of zeros, then the matrix is not invertible. So it's not possible, right? When it's invertible, we mean, is it possible to find a matrix B such that AB and BA are both equal to I? And we've shown that this is not possible when there's a row or a column of zeros. So that could be our answer. Okay, so sometimes to justify, you invoke a result from the book or from a previous exercise. So solution 1, no, since when a matrix has a row or a column, maybe we can put the more general result, row or a column of zeros, then it is not invertible. So it's simple as that. Okay, that could be our answer. What I actually want to show you in this video is maybe a second solution, less obvious but quite nice, because it relies on geometry, and without any surprise, it relies on linear transformations. Okay, so we're gonna look at matrix A as the standard matrix of a linear transformation, and we're going to see why we can't invert that linear transformation. So to invert that transformation, right, it means if we've got TA, we want to go back. Like, we want to find a transformation that essentially after right, we're trying to find maybe a T of B, so that if I compose T of A and T of B together, I get the a transformation that does nothing. Right, so if it be invertible, right, I could actually find a composition T of B, so that a transformation T of B, so that when I compose it with A, it's essentially every X gets sent onto X. Things stay the same. In other words, this transformation would be the transformation with standard matrix I. And we'll see that's not possible. Okay. So let's look at what happens if I apply this transformation to the vector x. X would be a vector of with 3 components, right? So 1, 2, 3, 0, 0, 0, 4, 5, 6. Let's apply this to X. Okay, well, what do we get here? We're going to get, okay, multiplying 1, 2, 3 by the components of X, we're going to get some number. I'm just going to put a star. It's going to be some number. When I multiply the second row of A with X, well, I'm going to get 0, right? Because 0x1 plus 0x2 plus 0x3 is 0. And then I'm going to get some number here. So essentially, what do I have? I've got a, okay, for instance, I could get this by multiplying it by X, 203. But essentially, it's going to be a vector where the Y component is 0. So it's going to be a vector or a point, okay, if we think about it, X, Y, Z. The Y component is a 0, so we're going to actually be in this XZ plane. So this guy here, this is part of the XZ plane, exactly. Because the Y component is 0. Okay. Now the XZ plane, that's a plane, right? So it has dimension 2. It's 2. And the X we had here, right? That was part of R3. R3 has dimension 3. So essentially, we start with a space of dimension 3. We apply T to it, T of A, and we end up with a space of dimension 2. So as you remember from a previous comment, with linear transformation, it's not impossible to increase the space of the object okay, by applying that transformation to that space. So if I map objects in a two-dimensional space using a linear transformation, T of B, at most I will have I will end up in a space of dimension 2 at most, okay, 2 or less. So it's not going to be possible to create a linear transformation that maps a space of dimension 2 to a space of dimension 3. Okay. So let's write this up. So since the xz plane is of dimension 2, it will not be possible to find a linear transformation that maps the xz plane onto R3, which has a higher dimension of 3. Therefore, A is not invertible. So I know that's probably not something you could have come up with by yourself, or maybe you did. If you did, bravo. But I wanted to show you that there are other arguments that are based on geometry that are kind of nice once we know how to use linear transformations.